today, we're going to talk about how to solve a differential equation when it's not separable. How do you get an answer? I know I can graph a slope field, but is there any way to get an actual answer to a problem? Well, actually there is, and it's called Euler's method. And Euler's method is a way to approximate the solution to a differential equation at a specific point using small delta x's. Okay? So the steps for Euler's method are to make a chart. The chart headings are you start with the ordered pair you're given. So that's x, y. Then you find delta y, which we'll talk about in a second. And your third column is x plus delta x, y plus delta y. On AP questions, they will ask you to show your work for how you got your answer. So you have to show a chart. You cannot just write some stuff down. You actually have to make a chart. All right, so you start with the beginning point that they give you. You plug those values in for x and y into dy dx. You multiply by the delta x, which is either given or they tell you to go from like 0 to 2 with 4 equal steps, which would mean you'd go by 0.5, or use 5 equal steps to go from something to something. So they either tell you what delta x is or they give you enough information to find. Now, to find delta y, we know that delta y means the change in y, and delta x means the change in x. So that's really dy over dx. So if I cross multiply, I get delta, I don't even know why I would cross multiply, forget that. I want to get what delta y is equal to, so that means I'd multiply both sides by delta x. So delta y would equal dy dx times delta x. That's what goes here. So as long as you remember this relationship, delta y is easy to find. So then you add your delta x to your x point, you add your delta y to your y point, and that's your new point that you start with, and then you do Euler's method again until you get to the required point that they ask you to find. So let's run through an example here. So let's say we want to do Euler's method to find f of 0.3. We're using delta x of 0.1. That must have screwed up whenever I typed that in, sorry. And we're starting at 0, 0. So my three columns are my point, delta y, which is dy dx times delta x, and then my new point by adding my delta x's and my delta y's. So, again, we're starting with 0, 0. So delta y is dy dx. Here's my equation for dy dx. Plug 0 in for y and 0 in for x. I just get 15 times delta x, and delta x is 0.1. So that would be 1.5 for delta y. So my delta y is 1.5. Remember, my delta x was given at 0.1. So the x that I started with was 0 plus my 0.1, comma, that shouldn't be a parenthesis. Y was 0 plus 1.5. So my new point is 0.1, comma, 1.5. So now I find delta y again. So I plug in x and y for up here. So we have 15 minus 3 times 1.5. All of that times my delta x, which is 0.1. And that should give me 1.05. So here I have 0.1 for delta x, for x, plus my delta x 0.1, comma, y 1.5 plus what I found for delta y. So my new ordered pair is 0.2, comma, 1.55. Find delta y, so 15 minus 3 times 1.55 times 0.1 is 0.735. So we have 0.2 plus 0.1 for x. And for y, we have 1.55 plus 0.735. So that means that f of 0.3 is approximately 3.285 by adding these together. So I have estimated the function without having a function. The closer the delta x's are together, or the smaller the distance between delta x's, the closer your answer will get, which we'll see in a few minutes how that works. Okay, so let's actually look at what a free response question might look like in BC calculus test. Morning.
Morning.
How are you?
Doing good.
Good. Is it going to bother you if I make a video?
No.
Okay, cool. So you'll notice that we're given the differential equation dy dx equals xy over 2, and that is separable. There is a reason for that, which we'll get to in a few minutes. So I have to write the slope field for the 9 points that are there. So I need to find the slope for negative 1, 1, negative 1, 2, negative 1, 3, 0, 1, 0, 2, 0, 3, and 1, 1, 1, 2, 1, 3. So when I plug in the x and y for x and y and dy dx divided by 2, here I get negative 1/2, here I get negative 1, here I get negative 3/2. These are all going to be 0. Here I'll get 1/2, here I'll get 1, and here I'll get 3/2. So my slope field looks something like, so we have negative 1/2, negative 1, negative 3/2. All these are 0. And 1/2, 1, 3/2. So it's symmetric on both sides. Now, that's part A. In part B, it says use that same dy dx, which was xy over 2, and use Euler's method this time with a step size of 0.5 to find or approximate f of 2. Okay? So, practicing Euler's method again. So my three columns are xy.
I'm bringing your...
Okay, so xy is my first column, delta y, which remember is dy dx times delta x, second column, and third column is x plus delta x, comma y plus delta y. So we start off with the initial condition of 0, 3. So if I plug 0 and 3 in for x and y, I'll get 0 in dy dx times 0.5 delta x gives me 0. So that means I start with my 0, but plus 0.5 for delta x, and 3 plus 0. So my new point is 0.5, comma 3. When I find delta y this time, I have 0.5 times 3 over 2 times 0.5, which is my delta x, and that's 0.375. So we have 0.5 plus 0.5, 3 plus 0.375, so our new point is 1, comma 3.375. Finding delta y, which is 1 times 3.375 over 2 times delta x, 0.5, gives us 0.84375. So I have 1 plus 0.5 for delta x, and 3.375 plus my new delta y, 0.84375. So my last point here is 1.5, comma, 4.21875. Finding delta y, I'm just going to do show you I'm not going to show the calculation. It's 1.5820325. You don't have to write that many decimal places. I just am, and you'll see why in a few minutes, I hope. So you had 1.5 for x plus 0.5, and I had 4.21875 plus my delta y, 1.58203125. So that means that's now 2, so f of 2 is approximately 5.8007. So remember, that's an approximate answer, not an exact answer. But this time we start with a separable differential equation, so that means we can actually find the answer and see how close our approximation is. So we have dy dx equals xy over 2. So I want the x's and the y's together. So if I divide by y, I get dy over y. Multiply by dx, I get 1/2 x dx. Now, why did I leave the 1/2 with the x? Generally speaking, it's easier to have the coefficient with the x, and it's easier if the coefficient is separate from the x. So I wrote it separately. Now I'm going to integrate both sides. The integral of dy over y is a natural log of the absolute value of y. Don't forget the absolute value. Equals, so when I integrate 1/2 x, I'll get x squared over 4. And then don't forget your cupcake. Okay? Now you do not want to find your c until you e both sides when you have a natural log. When you e both sides, you still have absolute value of y. Remember that when you add exponents, that means that came from e to the x squared over 4 times e to the c. E to the c is just a number, so we can call all of that still just c. So it's c e to the x squared over 4. We know that e is always positive, so the only way really this quantity can be negative is if c turns out negative. So now I plug in my initial condition. 3, the absolute value of 3 is 3, equals c e to the 0. So that means that c is 3, which means y is positive. So y would be 3e to the x squared over 4, or f of x is 3 to e to the x squared over 4. And I can approximate what? So if I want to now find the solution to f of 2, if I plug 2 in, I get 3e to the 2 squared over 4, which is really just 3e to the first, and I get 8.1548. Now, if you notice, those answers are not close at all. And the reason for that is because our delta x was 0.5. If you use a delta x that is much closer, you'll get a better answer. Okay, so they're far apart, but if I were to find f of 0.5, which was closer to 0.0, which was the given point, I'd get 3e to the 0.5 squared over 4, which is 3.1934, and to the 0.5 we saw was 3, so that's a much better approximation.